So hello everyone, welcome to the AEROSPACE channel, and my name Ujjwal Srivastava, and just I'm doing my master from IIT Kanpur. So let's start the class. So in previous class we did till here space trajectory and all things. I think hope you are understanding all the things. And then let me proceed next. So I think for this space dynamics we'll take on or 2 or 3 lectures more for 1 hour. So we'll complete it, then after we'll do then after we'll finish this as PYQs for different years. So we'll start from 2007 and this will end till 2024. Then let me start. So draw a figure. So basically till now we have built our basics for everything. Now we are basically going to the core of the space dynamics, that is especially for the circular orbit as well as elliptical orbit. So after some times I will derive velocity or something is related to the circular orbit. So let's start first. So now draw one figure. So now pay attention, this way it's please make very very pretty, you can say. Let's make an ellipse. Okay, it's fine. Little bit here, fine. Let us suppose this is your capital M, capital mass, right? Let's suppose here is your small mass. So from here to here, let us join this. So this distance are called as a RB. I'll tell you why I'm saying B. It is having some velocity. So let's see, it is B. Okay. The angle is here. See, now this is the point, and this is one orbit, right? If you want to go in the higher orbit, so we have to fire the rocket. So for the firing we have to burn our fuel. So that is why I am calling this distance as a RV. So this burnout distance, this velocity at which the rocket is burning for going to the higher altitude or higher orbit, that is called our burnout velocity. And the angles which are measuring for going to the another orbit, so we are measuring the angles from here only. This is our origin, you can say. This is our origin, you can say. So from here we have to mark theta. Theta is equal to 0 now. This is your B point, that means burnout point. Now at some time, let's suppose this mass went here. This mass traveled and just went here, and again it is having some distance. It is not burnout because already burnout has been completed, and this mass has gone to here, and this velocity is having the higher velocity than the BB. So there is some velocity of this particular mass, right? And now the angles are measured from here. So angles are measured from here. So from here to here, the angles are theta. Okay, this is basically your elliptic orbit. Elliptic orbit, where eccentricity is less than 1. That means the eccentricity of a conic. Again I'm saying, let's suppose initially the orbit was this, okay. That means I was having orbit here, if I want to increase my velocity and if I want to go one point to the another point, so I have to burn the fuel so that I can gain the burning velocity and I can increase my speed as well as increase my height. So if I burn the fuel, so I will get the burning velocity VV, and my speed will be uh, you know my speed will be the V after some time after burning the fuel. So this point at which the burning is getting completed, so this point is calling B, this is called burnout point, okay. And this distance at which the burning is happening, that distance is called as the burnout distance. And from here we are going to measure the angle. That means this theta is nothing but this angle, right. So this theta is basically this angle. So that is called the velocity and the mass and a small mass, the burnout distance, burnout velocity, this angle theta. Similarly we have to make for the, and these are going to basically this elliptic orbit we are going to discuss in a Kepler's law. When we will study the Kepler's law, first law, second law, third law, again we'll draw this same figure and we'll understand this in very neatly, how the the satellite is moving very fast and when it is near to the higher body or heavier body, why it is moving slow when it is far from the higher body or lower or heavier body. So we discuss all these things in a Kepler's law. Again draw one figure, because now we have to focus only on circular and elliptical orbit because we are not going to the deep space anymore. So the figure which I'm going to make now, which is available here, the same figure I have made. So let me take, okay, no, let us draw again. Fine, same thing happening. This is your capital mass M, somewhere this is your small mass, right. Then this is your distance, burnout distance, you can say RV. This is a burnout point. From here we are measuring the angle, so theta is equal to 0 here. If we are going to the another point, let's suppose here, then here it is burnout velocity VV, here the velocity will be your B, again the distance will be R, same thing, right. And this angles will be theta something, some theta value which can be radians or degrees, no issue. So this is your circle, theta equal to E equal to 0. Fine. Now draw parabolic or hyperbolic. Again we have to make one coordinate axis. This is pretty simple, so don't be confused, and it's very straightforward. They are not going to ask question about this figure, but only I'm telling you about this figure because of the better understanding or nothing else. But when you will study the Kepler's law or elliptic orbit, so we'll make the figure of this particular thing and we'll understand this very neatly. And after some time we are going to derive this, what is this velocity and all, right. So let us start. Let's suppose this is your M, capital M, okay. Now I have to make one parabola. Okay, let me make it neatly. Fine, it is okay. So let's suppose this is your R, this is your small m, okay. It is having some velocity, again a small m, right. It is a B point. So it is having some distance, that is vr. It is having some velocity, that is your vv. So from here to here at some distance r, it is having some velocity. The same story is for all. Again, we are going to measure the angle from here to here. This is your theta. Same story for this is your parabola. When E is equal to 1, this E is nothing but your eccentricity. Similarly for the hyperbola, okay fine, hyperbola like this, it is more opened. So again, this is your capital M, this is your some M at burnout point. Then again, this is your distance are called as the burnout distance, right? This velocity is known as your burnout velocity. Again, at some time, after some time, if you fire the rocket, so it will go at point M, and then it will be on some velocity. Then the distance will be vr, r. At this is your angle of the measurement, is your theta. This is called your hyperbola. So see, actually I was going fast in all this parabola, hyperbola or circle, because I have spent time on this to make you understand. So I'm going, actually the same story is for all, only the path is changing. So it's not that much important. Equal to 1. Now write some points now. It is very neatly figure, fine. Okay, right now circular and elliptical path, okay, right, of some point B. Okay, right, point B denotes the burnout of the rocket, of the rocket or any space shuttle which is firing, rocket booster you can say, or rocket, it's okay. And theta is referred as the angle measured from B point, that is a burnout point. Theta is chosen as 0, of course I told you, at burnout point, because we have to make the you have to take the theta from burnout point. That burnout point is your reference point, you can say, burnout, and C is your phase angle. As I told already, C is your phase angle. Now write one more point, that is a very beautiful point, is circular and elliptic paths results in an orbit about the mass m. What is this? Actually, if you want to stay in the orbit, like if you want to stay for any orbit, like your circular orbit or elliptical orbit or any type of orbit, if you want to revolve around this capital mass, or if you want to stay in this particular orbit, so you have to take a path of the elliptic, whether you can take the elliptical or whether you can take the circular. But if you want to escape from the particular thing, and if you want to travel into the deep space, you have to take the trajectory as a parabola or hyperbola. So same thing, it has a circular or elliptic paths result in a orbit. It is orbit, right, about the mass m. So if you want to stay in an orbit, so you have to be in the circular or elliptic path. Now, right? Okay, next one you can write. Whereas parabolic and hyperbolic paths results into result in escape from the earth. So I told you capital M. If you want to see, this is your this is your capital M mass, capital M. Let's suppose this is your capital M, right? This is your some satellite M or any rocket. If you want a satellite, of course, if you want to stay in this orbit of which is basically revolve, it can be circular or it can be elliptical, no issue. So if you want to stay in this orbit always, if you want to stay in this orbit, so you have to take a path of the circular or elliptic. But if you want to go from this, or if you want to escape from this orbit, so you have to take a path that is your parabolic or hyperbolic. Understood? Fine. This is the main difference. So every satellite which is revolving the earth, they are following the parabolic, they are following either elliptic orbit or circular orbit. Our space shuttles, international space stations which are revolving around the sun, around the earth, that is also in the parabola or also in the I'm sorry. The international space stations that are revolving around the earth or focusing to the earth, that is also revolving in the elliptic or circular only, right? So this is a case for this particular diagram. Now you write eccentricity formula in terms of the kinetic energy and potential energy, right? So write one very beautiful equation, that is E is equal to root under, please mark up this, 1 plus 2 h square plus h divided by m k power 4. You know all these things over here, right? One thing you don't know, that is, see, your h is nothing but your angular momentum per unit mass. You know already, right? This k is nothing but your gm, right? K square is nothing but your gm. So it's okay, you know everything. Only things you don't know, that is your h. So h is termed as it is also a difference of kinetic energy minus potential energy, but this potential energy will be in the mode. Only these things, because see, this h is depending, this is eccentricity is depending on this h, right? If this potential energy is greater than h will be less, then it will be some eccentricity will be less than 1 or something, we'll see now. So this h will be kinetic energy minus potential energy. This is your equation number, let me see, equation number 11. This is your equation number 11. Now see what happens to the h. Okay, let me write this, what is h or something. See, this k square is nothing but your gma. gravitational constant, okay, and this is your mass of the earth. If it is k to the power 4, so we have to write k to the power 4, that means gmv to the whole square. Okay, fine. What is this h? H is nothing but your r theta dot, you know already. Then what will be your h square? It will be r square theta dot square, right? And you know h is your, okay, let me write here. We know h is your difference of kinetic energy mod potential energy. Fine. Now let's see what happens if kinetic energy of the small mass is greater than the potential energy. Then what will be the trajectory of the particular thing, right? So if cases are arising, if kinetic energy is greater than the potential energy, then h will be, of course, greater than 1, which results here in this equation. See, everything is over here is positive. If this h is greater than 1, then it will be positive, right, plus this 1, so it will be almost greater than 1. You understood? It's a basic mathematics. See, if is your h is greater than 1, that means it's all